Today, again, we're going to use those Taylor series that we already know and manipulate them to get Taylor series or Maclaurin series for functions that we don't know the Taylor series for. And today we're going to start out with this example of using the Maclaurin series for sine to get the Maclaurin series for cosine. Remember, our Maclaurin series are Taylor series centered at 0. So we could do this for cosine. We did it for sine. We could take the derivatives of cosine. We could use the definition of a Taylor series and easily write the Maclaurin series. No problem whatsoever. But let's make our life a little bit easier and notice that to get to cosine from sine, I just take a derivative. So we know that cosine is the derivative of sine of x. And so what we're going to do is we're going to differentiate the power series. It's going to be easier if we don't try and start with the general term and take its derivative, because that gets a little messy. So let's just take the derivatives of the terms. This is where we differentiate term by term, and then see if we can find the general pattern. So I'm just going to rewrite that Taylor series for sine. So that's x minus x cubed over 3 factorial plus 5x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay, so now I'm just going to take the derivative of each term. This is term by term differentiation. That's what I mean by that. Derivative of x is 1 minus 3x squared. 3 factorial is just a constant, so it stays there. We're going to have 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. And so if we simplify these terms, the 3 will cancel out and leave us with 2 factorial. So we have 1 minus x squared over 2 factorial. The 5 and the 5 factorial will simplify. Sorry, that should have been a plus originally, to give me x to the 4th over 4 factorial. And then same thing, we'll have x to the 6th over 6 factorial. So I think we can easily see a pattern here. We're going to start from 0 to infinity. We have x to even powers, so we're going to make this x to the 2n. The same even power has a factorial, and then we just have a -1. It looks like to the n if we start at 0. Okay, so this looks like the Maclaurin series for cosine. Kind of a nice little Maclaurin series. I think that was a lot easier to do, taking those derivatives, than it would have been to find a lot of derivatives of cosine and then plug things in. But you might differ. You might have a different opinion than I do. So this theorem below tells us that we can take the derivative of power series and we can integrate power series. When we integrate, we get a constant of integration, so we do have to be careful about that. And the thing here is this tells us that the radius of convergence for the derivative or for the integral is the same as the radius of convergence for the original series. And so what that tells us is that the radius of convergence for cosine's Maclaurin series is infinity. So this converges for all x, which is awesome. Okay, so that saves us a lot of work. I like that. Okay, so let's do another example here. So in this example, I start out by giving you this fact. I notice that the integral of -1 over 5 minus x gives us the natural log of 5 minus x. And I want to use that to find a power series representation. Actually, last class, we could have done something a little bit easier to find the power series representation for ln of x minus 5, but we'll just do what this problem is asking us to do to get some practice. So I should start out by finding the power series representation for this guy, and then we're going to integrate it. So this one has a little bit of work to do. So we've got a negative out front. So we're going to have a -1. And then remember, we have to pull that 5 out. So we make that a 1/5. And then that gives us 1 minus x over 5. Okay. This is not a super pretty problem. I'm sorry, guys. So to write this Taylor series, we're going to have -1 over 5 times, times the power series. We're going to use the power series for 1 over 1 minus x, which is up here. So this Taylor series, we're going to replace all the x's with x over 5. So when I do that, what am I going to get? I'm going to get 1 plus x over 5 plus x over 5 squared plus x over 5 cubed, and so forth and so on. Okay. And now I'm going to rewrite this as -1/5 minus x over 5 squared when I multiply that 5 through. Then I'm going to have minus x squared over 5 cubed plus, minus, because I'm multiplying by that negative 1/5. Goodness, minus x cubed over 5 to the 4th. Okay, so that is this guy. That's the stuff inside the integral. Now I want to integrate this. When I integrate that, that will give me, this is very bad notation, guys. I'm sorry. When I integrate this, this will give me ln of 5 minus x. So again, I'm going to integrate term by term. Let me put my dx out here. So I'm going to get negative 1/5 x minus x squared over 2 times 5 squared. Remember that 2 came from anti-differentiating. Minus x cubed over 3 times x cubed minus x to the 4th over 4 times x. Yep, that was a 5, sorry. 5 to the 4th. And remember, when we anti-differentiate, we need a plus c. So I'm going to put my c over here, plus c. This gives me ln of 5 minus x. Okay, plus dot, dot, dot. We need to find our value of c. And an easy way to do this, an easy number to plug into this power series would be 0. So to find c, we're going to plug in 0 on both sides. So on the left-hand side, we're going to have ln of 5. All of these terms are going to be 0, so we're just going to be left with c. So that tells us our c is ln of 5. And so let's just replace c by ln of 5. Okay, if we were trying to write the summation notation for this, we would leave the ln of 5 just out front because it doesn't look like it's going to follow any pattern. The pattern for these guys looks like if I start at 1 and go to infinity, I'm going to have negative x to the n over, it looks like n times 5 to the n. Looks like my pattern. Okay, sorry, that last example kind of had a lot of pieces in it, but the goal with both of these things is to notice that, first of all, I can take the derivatives of power series, and I can take the antiderivatives, the integrals of power series, and when I do either of those, I'm doing the differentiation term by term and the integration term by term as well. So we'll get some practice with this in class.